We're going to keep building on the themes of thinking about nonlinear dynamics or nonlinear systems of differential equations and how to use solution techniques from linear systems of equations to help us understand the qualitative features and behaviors of these nonlinear dynamic systems, or boundary value problems for that matter. So the case we want to start off today is understanding what are called predator-prey models. These are more than a century old in terms of thinking about modeling interacting species, but there's some just very nice concepts in this predator-prey system that teach us a lot about what nonlinearity does to drive dynamics and interactions and the kind of possible behaviors you can get out of this. This is for my course on advanced differential equations. You can find the notes on the archive. They just were put up. So let's talk about predator-prey models. So the concept here is we want to start coming back to what are the range of possible behaviors of systems of nonlinear system of differential equations like this. X dot equals f, y dot equals g. Okay? And so part of what we did in the last lecture was to look at what are the possibilities when you have linear dynamics, and we showed that there's 5 canonical things that can happen there. And so part of what we want to do is build upon that and start talking about general methods for handling nonlinear systems like this for some arbitrary f and g. Okay, so what are we going to do? Well, the fact is we're going to look at 2 main concepts, and this is exactly what we did previously, is with these 2 concepts, you can really make a lot of progress in understanding systems. One is to look at where the equilibrium solutions are. In other words, the equilibrium happen when x dot is equal to 0 and y dot are equal to 0. And what that tells you when they're both simultaneously 0 is that is a spot in the system where you are at rest or equilibrium. Nothing is happening because the derivatives are 0. This is very equivalent to finding minimax of functions, right? We know that minimax are functions. You set the derivative to 0. These are special points. Same thing here for equilibrium, is both x prime and y prime are 0 simultaneously. This is a system at rest. Nothing is changing in time. Once we find these equilibrium solutions, we want to understand their stability. And the stability is basically a local analysis around that equilibrium point. So this is going to represent much of the efforts in this in our viewpoint here, is to try to think about local analysis, so perturbation methods, approximation techniques that we can use linear methods to solve, because that's actually the only kind of problems we can solve closed form are typically linear problems. So can we take these nonlinear systems, look at locally near equilibrium points, and look at the linear analysis there, and then say something about the global behavior of the system. And in fact, that's exactly what we're going to do. So it's all about the art of approximation. And that's what we're really trying to think about here is, and I want to approximate these nonlinear systems with a linear system, because the linear systems, I have recourse to analytic solution techniques that I can just write down with pen and paper and say quite a bit with. So let's start first with the idea of equilibrium in the system. Remember, I had x dot equals f, y dot equals g, and what I'm interested in is pairs of points x naught, y naught, such that x dot is equal to 0 and y dot is equal to 0. So this is what they're going to satisfy. F is equal to 0, g is equal to 0. So this is your equilibrium point. If you can find a pair of points, x naught, y naught, that make both these 0, these are very special points in the system. And in fact, around these points, if you can understand the behavior around these points, then you can understand everything that happens in this nonlinear 2x2 system of differential equations. Okay? So that's the claim. And so how are we going to do that? Well, we're going to start looking at the stability of these points. So once I find these equilibrium points, the idea to understand stability is to do something like this. Perturb around that state. In other words, x is x naught plus x tilde. Y is equal to y naught plus y tilde. Remember, x naught and y naught is the equilibrium point. So x tilde and y tilde, I'm going to make them very small. So they're going to be very small quantities. So what they represent is you being very close to the equilibrium point and understanding what happens to x tilde and y tilde if you are close to the equilibrium. Now remember, we're going to approximate this with a linear system. And linear systems basically are going to have exponential solutions. And so solutions are either going to blow up to infinity, which means this would mean it's an unstable point, or they're going to go to 0, which means it's a stable point. Now there is the case in which the eigenvalues around the system are purely imaginary, in which means you'll just oscillate around that system, around this fixed point. Okay? And that's what we found last time in the pendulum. But those are the behaviors, and that's started to get our concepts of stability in our mind, which is it's all about what is the long-term behavior of x tilde, y tilde if I start close to this equilibrium point. So the way we're going to do this is basically using Taylor series expansions. And so one way to put this in is to say, well, if I'm very close to this point, then x is equal to x naught plus x tilde. Y is equal to y naught plus y tilde. And so I put that back into my original system. And when I plug that in, remember I plug it in on the left too, x naught and y naught are constants. So when I take their derivative, it's 0. So all I have is x tilde prime, y tilde prime. So this here is what I want to do is take this system and linearize it near this point x naught, y naught. And what does it mean to linearize? Well, what I want to do here is Taylor expand each of these functions f and g. And what I'm interested in throwing out are terms that are like x tilde squared or x tilde cubed. In other words, if x tilde is small, then x tilde squared is much smaller. X tilde cubed is much smaller than that. And I want to throw away all those terms and just keep the most important term, which is the x tilde. And that's the process of linearization. And how do you do this? Taylor series expansions. So consider the following. F of x naught plus x tilde, and you expand. Well, you have f of x naught plus x tilde f prime x naught plus x tilde squared, x tilde cubed, and so forth. Now, the way to think about this is if I'm at an equilibrium point, then the idea is that f x naught at the equilibrium, this is 0, so this is going to drop out. This first term will just be 0. Then I have x tilde f prime at x naught. And then these terms here have x tilde squareds, x tilde cubes, and so forth. So presumably, if x tilde is small, these should all be much smaller than this term here. And that's the one I want to keep. And this is the concept of linearization, because now it's basically a linear term in x tilde times this here, f prime x naught. And often it's called the Jacobian. So let's do this for the bigger system here, which is let's Taylor expand this all, both in x and in y. And so what you find is x tilde prime is equal to f x naught y naught, that's that leading order term, plus x tilde, this is the partial with respect to x, evaluated at x naught y naught, partial with respect to y, evaluated at x naught y naught. And then same thing here, which is expand, I get g x naught y naught, partial with respect to x at the equilibrium point, partial with respect to y at the equilibrium point. Now notice f x naught y naught and g x naught y naught, these are 0. That's the assumption of being at equilibrium. So these are going to drop out, and those are the terms you have left over. And I've dropped everything with an x tilde squared or x tilde y tilde or x tilde cubed. Anything that's higher order is now gone. It's presumably smaller. At least if x tilde and y tilde are both very small, that should be a good approximation. That is this idea of perturbation theory in a linearization around each of these equilibrium points. So what do I get? Well, if I take this linearized equations, here's what it gives me. And this is the linearized equations for what is the dynamics of x tilde y tilde, and it's given by this matrix A, which is a 2x2 system here, which is the Jacobian. And notice what it is you take the f and the g's and you take partial derivatives of them with respect to x and y, evaluate it at the equilibrium, and that's going to fill in with this matrix A. And all I care about now that I have a linear system is what are the eigenvalues of that matrix? Because once I understand the eigenvalues, it's going to come into the form of 5 prototype forms that we discussed in the last lecture. I could have a saddle, spiral stable, stable spiral, center. There's different possibilities depending upon what the eigenvalues are of this linearized equations. Okay, so let's make up a model. Let's get more specific. Let's call it the generalization of what we want to do. Is if you give me some generic system f and g, then you can go compute these things. And I want to do this now in the context of a very specific model. And this is a Predator-Prey model, or an interacting system where the interactions are nonlinear. So we call them a Predator-Prey system, but really in some sense they're just what happens if you have two interacting species or competing entities. How do they interact with each other and produce some kind of understandable interpretable dynamics that we can get our head around to understand what's going on in that system and have a good qualitative understanding with analytic techniques. So the Predator-Prey system is really based out of ecological considerations, and it's a very nice way to framing to think about things. We start thinking about, for instance, a prey, and I often think about, for instance, wolves and rabbits. So, the X is going to represent, for instance, the rabbits. This is going to be the prey. So the wolves eat the rabbits, but the rabbits left to themselves, what happens? Well, the rabbits can feed off everything. Presumably, they can eat all these plants, and so in their natural environment without a predator, they would just simply have an exponentially growing population. So that's what this model here tells you. dx dt equals ax. So a is in some sense the growth rate of the rabbits, right? So left to themselves without a natural predator, their population would just simply exponentially grow. Okay? And this is a common observation for species without predators and essentially infinite resources. They will reproduce, they will grow exponentially. Human beings, rabbits, so forth. What's more interesting is when you have pressures then from the environment to sustain that growth, and that you can build models around that too, but for right now we'll just consider this, that rabbits have lots of space, lots of vegetation, they're just going to grow. So this is our prey. The opposite is true for wolves, the predator. The predator, in the absence of the prey, right? We don't really have vegan and vegetarian wolves. They like meat, and they're not going to apologize for that. They're just going to go eat like tasty bunnies. But if there's no bunnies to be eating, then the dynamics is given something like this. The population would simply dwindle and die away because they would not have a food resource. They would not be able to reproduce, they would starve, die. And so what this would tell you is that they have an exponentially decaying population. dy dt is minus cy. So c tells you a little bit about their decay rate. How long would they survive without having resources to live by, which are rabbits around. Okay? So this is sort of these two different species, and now we're going to put them in an interaction. And the interaction is going to be the following. The introduction of wolves to the bunnies, or rabbits to the prey, is going to be negative. It's, in other words, now they can get chased and eaten and die because of the presence of a predator. The predators, the interaction of having rabbits is going to be positive for them because now they have something to eat. And so if there's a lot of bunnies around, they can eat, have families, continue chasing these, have a good resource for food. So it's going to be the opposite for the two species. So one way to model that is to come up with and this is what historically people did, is came up with very simple modeling paradigms for how this interaction might go. It's some kind of nonlinear interaction, and it's of opposite sign for the two cases. So here, there's a minus sign here for the prey, which is it's minus alpha xy. So in other words, here we make a very simple nonlinear model, which is if I have a lot of bunnies and a lot of wolves, I'm going to have a lot of damping. This is going to be, in other words, my rate of change, dx dt, is going to go down from the presence of having wolves. Okay? And it's going to go down even faster if there's lots of bunnies because they're going to be able to feed and have a very good environment for their for their sustaining their population. So this is going to be a negative. It's going to decrease the population of the prey. Whereas here in the predator case, it's a positive sign, which means dy dt is going to go up. So in other words, you're going to have a positive interactions, and your population can grow in the presence of prey. So it's a very simple model, heuristic, qualitative. People very early on in trying to model population and ecologies, this is a very difficult problem, but they try to write down simple models to understand how would such systems interact. What are the kind of behaviors of such systems? How can we understand the fact that there is stable populations oftentimes of predators and preys, or oscillating populations which have been in observance also as well? How do we understand these phenomena that we observe by counting predators and preys, and how do we write down models to sort of increase our understanding of this process? So here's a simple model, this very simple predator-prey. And just like before, we're going to look at the concepts of equilibrium and stability. So equilibrium is given, there's two equilibrium points in this system. So I can come back to here and say, when is dx dt and dy dt 0 simultaneously? And it turns out there are two fixed points. Fixed point number one is when you're at 0, 0. In other words, the origin. There are no bunnies, there are no wolves, right? Which is stable. It means nothing interesting would happen in that case because there are no predator and no prey. Okay? There's also this one here, which is x and y. This is c over alpha, and this is a over alpha. In other words, there's some equilibrium point which involves a non-zero number of rabbits and non-zero amount of wolves. Okay? And so that's the value of it there, x and y. Okay? So this will give us, this is an interesting one for us to consider, because in some sense you want to understand how would these two populations sustain each other, right? Because the wolves would eat the rabbits, keeping their population from growing to infinity. But if the rabbit population dies off, then the wolves aren't going to have so much to eat, so their population would decline as well. And so how do we understand it? And this equilibrium point is going to be really critical to understanding this process. So let's start off with the simple calculation first, which is let's understand the dynamics near the origin. Remember, this is all based on local analysis. So at the origin, we can say, all right, this is 0, 0. We can take the f and the g. Remember, what we have to compute is we have to compute this Jacobian. In other words, the partials of f and partials of g. This is what f is. This is what g is for this predator-prey system. So f of x can be easily computed. There it is, f of y here, g of x, g of y, and then you plug in the values 0, 0, and then you can compute all this out. So that's as simple as it is. And this is your linearized system around the origin. So we're doing a local analysis around this equilibrium point, which is the 0, 0 point, which would be no wolves, no bunnies. And this is, in fact, your linear system right there. Okay? And what we can do with that system is look for eigenvalues. And the eigenvalues, there's one positive and one negative, and they're both real. So this is a saddle. So we have a saddle point at the origin. Okay? And we can also compute the eigenvectors corresponding to each of these different eigenvalues. So the eigenvalue lambda equals a, if you go back and you put this value into the eigenvector problem, you can work it out, and you find that your first eigenvector is in the direction 1, 0, and lambda equals minus c is in the direction 0, 1. In this direction, it's growing like e to the at. In this direction, it's decaying like e to the minus ct. Okay? So one direction is dying, one direction it's growing. All right. So what does that look like from a phase plane? Well, here's what the phase plane looks like. Something like this. And what I'm going to argue is this makes a great deal of sense. So here's the origin, 0, 0. Here's your predators. Here's your prey. And what we're looking at is the case when, if you have some high number of predators and, again, a low number of prey, then what happens? Well, the predators don't have anything to eat, so they start to die off. Okay? And then what happens to the prey population? Well, as all your wolves start to die off, the prey or the bunnies have a very favorable situation, and their population starts to grow. So it goes out here. So linearly, this makes a lot of sense. Near this point, the wolf population or predator population dies, and in the direction of the prey, it starts to grow. So first what you do in the saddle is you come down to this, you get sucked in down here towards this regime here, which is wolves are starting to die off. And as all these wolves die and their population goes to zero, it's a very favorable situation for the prey, in other words, the rabbits, and they start to grow. And so you get this kind of dynamics in this phase plane. So that's the first equilibrium point. This is the local analysis around there. That's the kind of behavior you get near that equilibrium point, 0, 0. Now remember, we have a second one. Here it is. This is where we have a non-trivial population of rabbits and wolves, or predators and prey. And so again, we can compute the Jacobian. So we can take the Jacobian and plug it in around there. And here's the calculation of these partial derivatives of f and g in terms of with respect to x and y, evaluated at this point. And it actually comes out very simply, and it gives us now this eigenvalue problem. Or actually, sorry, this first order differential equation for which we can compute the eigenvalues. And the eigenvalues to this, in fact, are purely imaginary. So in other words, what this tells us is that when we're near this equilibrium point, we are basically oscillating. So this is an interesting case here. So now what happens is you're basically your population of rabbits and wolves are in fact oscillating in time relative to each other. And so one way to compute this is you can compute the eigenvectors, and it'll kind of give you some idea of this. The eigenvectors, you plug back in the eigenvalue to the eigenvector equation, and here's what your eigenvector looks like at the end of the day. You can just plug that in, you work it out, there's an eigenvector. Now the one thing is that we might want to represent these eigenvectors in real form, or write down the solutions in terms of real solutions, because we don't usually think about having imaginary populations of rabbits or wolves. So we can always write down, instead of e to the I something, you can write it down in terms of cosines and sines, because that's what they really are. Okay? And so in the real form, you just simply take your eigenvector times its eigenvalue, you multiply it all out, and what you find out is when you do this, there's a complex conjugate pair where there's a plus I and a minus I. And so you can basically rewrite it into terms of two linearly independent bases, which is a sum and a difference of these. And what happens is that plus I and minus I cancel out, and I can get two real solutions. One of them looking like this, and you can see it's cosines and sines that are oscillating, and the other one looking like this, again, sines and cosines, with this square root AC as the frequency. Okay? So if I go back to my picture, remember this was the phase plane we had done previously. This phase plane here was near the origin. And now this is what this phase plane looks like around this non-trivial point that we found as an equilibrium point. And notice here, everything's oscillating around here. Okay? So this is kind of an interesting thing. When you're near this equilibrium point, what happens is, as it's kind of this interesting interplay, as the rabbit population goes up, then the wolf population goes up. But as the wolf population goes up, then the rabbit population starts to decrease. But as it decreases, then the wolf population decreases. Well, as it decreases, the rabbits start to go back up. So what you have here is this interesting cycle of the rabbit and wolf populations interplaying with each other, in at least this model, to produce this periodic behavior. In other words, there's only one equilibrium point. You'd have to have exactly the right number of wolves and rabbits to live here, but generically, you're sort of somewhere around some of these cycles that are there, these limit cycles. And by the way, this gives us enough to do a global analysis. Remember, the local analysis was done in this corner and around that point. Now, if we just do simulations of this system, right, so it's a nonlinear system, you can just run this in some ODE solver. This is actually what the dynamics looks like. And you can see I have a fixed point here, And here I knew it was going to look this way, right? Because in fact you did the analysis, and so you know that the global phase plane was really based upon your local analysis of the two equilibrium points. And so this is an interesting dynamics for this Predatorprey system because we understood almost all of it qualitatively just by looking at the equilibrium and their stability. And indeed, we see this behavior borne out in the full nonlinear dynamic simulations. And in fact, if you were to take this and write, instead of looking at the phase plane, just look at the actual time series of the population, here's what it looks like. So the predators are here, the prey is in the lighter lines, and so what you're seeing here is essentially a dynamic that really makes a lot of sense, and in fact that has been observed in actual collections of trapping data in near Lake Huron, where they were actually keeping records of type of rabbit and lynxes, and they had very much a pattern like this. So this isn't just some fictitious thing. It seems that in biology you do actually see some of this borne out in ecological systems. And so what happens here is, notice what happens here. When the rabbit population starts to spike and go up, accordingly the wolf population starts to go up. But as the wolf population starts to very much increase, they start to decimate the rabbit population, which starts to plummet. But as the rabbit population plummets, then it becomes very competitive and difficult for the wolves, and so their population plummets. But then, if the wolf population plummets, the rabbits are now favorable again, so they come back up, which means the wolves come back up. So there's this cycle of a lag time where the wolf population is lagging whatever's happening to the rabbits. If the rabbits go up, the wolves start going up, but because as they go up, the wolves go up, it makes it less favorable for the rabbits. They start to go down, and which means it's very unfavorable for the wolves at that point, so they start to go down. And this is the kind of pattern that you see in some of these ecological systems. And again, this is the nonlinear dynamics, right? And oftentimes we can't write down closed form solutions to nonlinear dynamics. But what we can instead here is understand most of it by writing down solutions to two linear systems and constructing a global behavior from that, all based upon this idea of perturbation theory. Okay, so again, we come down to this idea, the phase plane dynamics for these nonlinear. I want to understand nonlinear systems ultimately, so the phase plane helps me do that, and so this global analysis, which is qualitative, we get it from looking at the local behavior from the eigenvalues, and it's, it's all based upon this idea of perturbations. And that's going to be a lot of the theme for the course, is thinking about perturbations and approximating nonlinear systems with linear systems in such a way that we can draw out a lot of understanding from the system. So that's where I'm going to leave you, and we're going to start and we'll have more formal lectures on perturbation theory, but also just here we're talking about time-dependent systems. We also want to talk about boundary value problems, which are another form of differential equations, and so we want to understand that as well as the time-dependent problems, because ultimately towards the end of this class we'd like to do spatial temporal systems, which have both space and time jointly together for our understanding.